Hey guys, today we're going to be talking about how to make a full adder in Minecraft. I'm going to go over how to make different kinds of logic gates and how they can be put together to make a full adder. So let's start by talking about the conventions that I'm going to use in this video. So the words on, true, and one all mean the same thing and refer to the lamp being on, being lit. The words off, false, and zero also mean the same thing and refer to the lamps being off. So in a real-world application, you can think of as on, true, and 1 being your high voltage. Your 3.3 volts, your 5 volts, your 7.5 volts, whatever you want. But that's a high voltage, where off, false, 0 would be your low voltage, 0 volts. So let's start with the easiest gate, which is no gate at all or a buffer. The logic table for this is really simple. If we have a 0 as our input, we want a 0 as our output. And if we have a 1 for our input, we want a 1 for our output. If we have our input here and our output here, how can we get it so that our logic table reflects what we see for our input and output? Well, it's pretty simple, right? If the input light is off, the output light is off. If the input light is on, the output light is on. We can just build a straight wire. And actually, in practicality, it might look something more like this, because this would represent just like a wire. This actually is a lot more like a true buffer. And a buffer does exactly what it does in Minecraft. It just delays time between when the redstone is flowing. And this is what our buffer gate looks like on a diagram. The next gate we want to build is the opposite of a buffer, or a NOT gate. Our truth table for the NOT gate looks much like the buffer, except opposite. So what we want is we want the output to not be the input. So if we have an input of a 0, we want an output of a 1. And if we have an input of 1, we want an output of 0. This is what the symbol for our NOT gate looks like. You notice it looks a lot like the buffer, except it has this dot on the end. So you can think of the dot on the end as the actual NOT gate. So it's the same as a buffer, except it's inverted. It's the inverse of a buffer. Here we have our input and our output. We think about how can we get it so that when this light is on, this light is off, and when this light is off, this light is on. Well, a redstone torch is on until it's turned off, right? It acts as a source until it's turned off, and now it's no longer a source. So there we go. The redstone torch is in of itself already pretty much a NOT gate, an entire NOT gate. So then let's check our behavior. If input is a 0, output is a 1. Input is a 1, output is a 0. Great, we did it. The next gate we're going to want to build is an OR gate, and an OR gate looks like this. Let's take a look at the truth table for an OR gate. So what does OR mean? What do we want to see for our behavior for this? Well, OR is either or, right? One or the other. Or, in the case of logic, can also mean both. So we only want the output to be true, which is 1, when at least one of the inputs is true. So let's take a look at our inputs. 0, 0, well, neither of those are true. So that means that our output is also false. Next we have a 0 and a 1. Well, at least one of them is true, so that means it's true. A 1 and a 0, that's also at least one true. And a 1 and a 1. And this always confused me, but in logic, it's at least one must be true. So a 1 and a 1 still results in a true. So now that we know what we want from our behavior, we have our 2 inputs and our 1 output. So thinking about our behavior, we always want the light to be on, except when both lights are off. Well, if you think about it, both lights are off right now, and the light's off, so we got that one done. And then we only want the light to be on when at least one of our lights is on. Well, because of how we know redstone works, these will combine together. Oh, whoops. So if one of them is on, the output is still on. If both of them are on, the output is still on. And if the other one is on, the output is still on. And of course, if both of them are off, it's still off. So it looks like our truth table checks out. So there is our OR gate. The next gate we're going to talk about is the NOR gate. So here's the symbol for the NOR gate. You'll notice it looks exactly like the OR gate, except with that bubble again that we saw on the NOT gate. So this means that it's an OR gate, but with the outputs inversed. So when we look at our truth table, we want it to be exactly like the OR gate, except completely inversed. So when we had 0, 0, we had an output of 0. So if we inverse that, we get an output of 1. And for the rest, we had 1s, so now the rest will be 0s. We can also take a look at the picture, and that gives us a hint on how we can build our OR gate. So we're going to build an OR gate, and then just add a NOT gate to it. And let's check our behavior. 0, 0 should be a 1, which it is. 0, 1 should be a 0. 1, 0 should be a 0. And 1, 1 should be a 0. The next gate we're going to talk about is the AND gate. For here, what we're looking for in behavior is we only want our output to be true if 1 and 2 are both true. So if we look at the only situation where we have 1 and 1 is in this last case. So this is our only output which will be true. So here's our finished AND gate. Let's test our behavior to make sure it complies with our truth table. So we have 0, 0 is a 0, 0, 1 is a 0, 1, 0 is a 0, and 1, 1 is a 1. So great, it works. The next 2 input gate we're going to look at is the NAND gate. So you can see the symbol for the NAND gate is the same as the AND gate, but with that bubble again. So this is going to be the AND gate, except the reverse. So where we had 1s in our AND behavior, we have 0s, and when we had 0s, we have 1s. So we could apply the same strategy that we did to the OR gate by just making an AND gate with a NOT at the end. And that will work. However, if you notice right here, we actually have 2 NOTs right next to each other. And if you say not, what you're really saying is. So let's look at our behavior for just this moment really quickly. Right before we have the not. 0, 0 is a 1, 0, 1 is a 1, 1, 0 is a 1, and 1, 1 is a 0. So actually, without these NOT gates, we already have our desired behavior, which is kind of interesting because the NAND gate, the not AND gate, is actually simpler than the AND gate. And this is actually true of real life too, of real and NAND transistors. So the last gate we're going to talk about is the XOR gate. That stands for exclusive OR. This one's a little bit more complicated, but it's one of the most important, especially when it comes to constructing the adder. So the exclusive OR means that it is either one or the other. It cannot be both. So when we have our 1, 1, where in the normal OR that would be true, we now have false, because it cannot be both. It must be one or the other, like in these 2 cases, where it is either one or the other, and not both. In this one, it's neither, so that's also false. And here's the symbol for our XOR gate. It looks kind of like the OR gate, but has that line that makes it different from the normal OR gate. So this XOR gate is actually not my design. I got it from Minecraft101.net because the XOR gate is pretty complicated and I didn't want to sit here and try to figure it out. I built my gates in a way that I think is easier to see what's happening and is in a way that I think is more intuitive. This one is optimized so that it takes up as little space as possible, which will be nice when we are building our adder. So let's just make sure that Minecraft101.net didn't make a mistake, and let's check our behavior. So we have 0, 0 is a 0, 0, 1 is a 1, 1, 0 is a 1, and 1, 1 is a 0. So perfect, so that's working. I want to take a minute and talk about why I think that this gate is one of the most important. If we think about our logic table in terms of adding, what we see from the XOR behavior is that it actually already is in itself an adder. 0 plus 0 is easy, that's 0, and our output is also a 0. Our next one, 0 plus 1, is also 1. 1 plus 0 is 1, and our output is 1. And then 1 plus 1. 1 plus 1 is 2. But we're using binary numbers, and 2 doesn't exist. So what is 2 in binary? Well, 2 is 1, 0. There are 10 types of people in the world, those who understand binary and those who don't. 1, 0 is 2. So actually what we're seeing from that 1 plus 1 is the last bit, the least significant bit, is actually our output. And we have an overflow bit of 1. If you've done any programming, you're familiar with overflow error, and that's what's happening here. We only have a 1-bit output. So we're getting that least significant bit, that 0, and we're losing that 1. So 1 plus 1 is still 1, 0, but we're only seeing half of that answer. So when we talk about how we want to construct our adder, we know that the XOR gate is already going to give us our least significant bit. So with just our XOR gate, we already have half of our job done. So let's think about how can we get that overflow bit? Well, let's make another truth table. So how do we find our overflow bit? Or I'm going to call it our carry bit. Let's see, if we take 0 plus 0, if we think about that in 2 bits, that's 0, 0. So we know that that second 0 comes from our XOR gate, but that first 0 is going to be in our carry bit. 0 plus 1 is 0, 1, so that first bit is a 0 again. 1, 0 is 0, 1, and 1, 1 is when we get that overflow, that 1, 0. So our carry bit will be a 1. So in order to find our carry bit, we want a gate that gives us 0, 0, 0, 1. Well, what gate gave us 0, 0, 0, 1? It was the AND gate. So actually, in order to find our carry bit, all we need is an AND gate. So let's test this and make sure that it still works. We have 0 plus 0 is 0, 0. 0 plus 1 is 0, 1. 1 plus 0 is 0, 1. And 1 plus 1 is 2, is 1, 0, 2. So our circuit works. This is in itself a 1-bit adder. And this is actually called a half adder. So if we wanted to continue and add another bit onto our adder, let's see what we can do. Let's take a minute to talk about binary addition. So when we want to add two numbers in decimal, let's say 19 and 12. We say, okay, 9 plus 2 is 11. So we put our ones digit down here, and we carry our tens digit up here. And then we have 1, 2, 3, and we get 31. The same is true in binary. Say we wanted to add these two numbers together. 1 plus 1 is 2, which in binary would be 1, 0. 1 plus 1 plus 1 is 3, which is 1, 1. 1 plus 0 plus 0 is 1, and 1 plus 0 is 1. This is important to grasp in order to understand how our adder is going to work. So what we've just built, our half adder, is this part of the process. We've also found this carry bit here. So what's our next step? Well, our next step is to add what would normally be the tens place, and in binary we call the twos place, is to add all of the digits from the twos place. So what we're actually now adding, instead of 2 bits, we're adding 3 bits. So for our next step in building the adder, we actually have to add 3 bits together instead of just 2. And we essentially do that by adding 2 bits and then adding another bit. So I'll show you how that's going to work. So we already have our least significant digit done. Here's our carry bit. And first thing we're going to do is add our 2 new bits. So now we have our output from our first 2 bits. We want to add it together with our carry bit. So now we have our second least significant bit along with our least significant bit. But the question is, what if we wanted to add yet another bit? We lost our carry bit. So how do we calculate the new carry bit? Well, let's look at yet another truth table. So imagine that we're adding all of these numbers together. And remember, we're trying to find the carry bit. So that'll be the first digit. So I'm going to write out both the digits, but what we're really concerned about is that first digit. So 0 plus 0 plus 0 is 0, 0. 0 plus 0 plus 1, 0 plus 1 plus 0. So to find the carry bit for the next step of the adder, what we're going to need to do is take this carry bit and it together with our one bit sum, and our bits together and OR those two together. And now we actually have a 3-bit adder. And let's test it. Remember that these blocks both stand for a 1. The lamps represent these 2 bits that are in the red box, and they both have a value of 1. So we have 0 plus 0 plus 0 plus 0 is 1. 1. 2. If we turn both of these off, remember each of these blocks, each of these lamps, each has a value of 2. So we get 0 plus 2 plus 0 plus 0 is 2. 2 plus 2 is 4. That's 1, 0, 0. That's 4 in binary. 2 plus 2 plus 1 is 5. 1, 0, 1 is 5 in binary. And 2 plus 2 plus 1 plus 1 is 6. 1, 1, 0. So we can count all the way to 6 with our adder. So this is a full adder that I actually made earlier. I think it's a little bit cleaner, a little bit more compact, so I wanted to use it for this example. This is actually a full adder, and is not the half adder that we made before. So you can see it actually has a C0, a carry 0 input, so that you can actually choose to include a carry bit even without having added anything already. And this actually comes into play when you want to turn your adder into a subtractor, but that's beyond the scope of this video. And this type of adder has a name. It's called the carry ripple adder, because every time we add a bit to how many bits we want to sum, we are sending a carry bit across the line, down the line. That's why it's called carry ripple adder. And the best thing about a carry ripple adder is this. And just like that, we've added another bit to our adder. That's fully functional just by copy and pasting. You can keep copy and pasting your circuit over and over again and just adding more bits. And this is true when we're talking about the physical adder as well. It's a lot easier to manufacture something if all the parts are identical. However, the drawback to that is that if we start flipping switches, you'll notice there's actually delay. You saw it there. See how there was a flicker? For a second, it actually gave you a wrong answer. It didn't give you this answer or this answer. Wait. It actually, for a second, gave you a completely different answer. And when you change a bit down here, it actually takes a decent amount of time before that far, far away bit changes. So the downside to the carry ripple adder is actually that it's kind of slow. So the carry ripple adder, easy to manufacture, but not very efficient. Well, thank you guys so much for watching. I hope you learned something, or at least understand something a little bit better. I hope you can have a visualization maybe now in your head for how adders work, and maybe the physical components that are actually going into them. And I hope you have a great day. Thanks. And 0 all mean the same thing. On okay. So in a real world application, you can think of as on, true, or 1 equaling high voltage. So your 3.3 volts. Please, dude. This man is ruining my video. Hello?